So hi, everybody. I'm Julie Lavache-Clarondo. I'm a faculty at University of Montreal. And today I'm going to be showing you some new observations that we've obtained on the Perseus cluster of galaxies. And I'll be showing you how these observations are really providing a unique window into understanding how radio jets heat their surrounding gas, but also how they can trigger local instabilities that cause a small fraction of the gas to cool, condense, fall back into the black hole, reigniting the feedback loop. And so essentially creating a really efficient self-regulated loop. Okay, so just to make sure everybody's on the same page, I just want to remind everybody here when we talk about black hole feedback, we usually have these two different modes. Quasar feedback, where the black hole is accreting at very high rates and where most of the energy comes out in the form of winds or radiation. And then you have radio mode feedback, where the black hole is accreting at low rates. And here the energy comes mostly in the form of radio jets. And so I'll be focusing on this today. And it turns out that the best place to understand this kind of feedback and understand in detail what these radio jets are actually doing to their surroundings is in galaxy clusters. Let me show you why. Okay, so this is one of the best examples, one of the nearby massive clusters. So Perseus, you have at the center here the brightest cluster galaxy. This galaxy harbors an AGN, which is generating these radio jets. Now, normally, if you had this galaxy outside of a cluster, the galaxy and the black hole may be driving these radio jets, but it would be really difficult to understand what these jets are actually doing to the surrounding gas, because the surrounding gas is much more difficult to see in isolated galaxies. In clusters, the gas that surrounds the central galaxy is called the intracluster medium. And this is shown here in blue. And it's much denser, so we can easily detect it with current telescopes. And this is what makes clusters so fantastic for understanding how radio jets interact with the surrounding gas, because we can literally see these jets pushing away the gas, creating these large cavities, doing mechanical work, and having an impact on the gas. Now, it turns out that these radio jets appear to be really efficient at keeping this gas hot. If not, we would see massive starbursts at the center, which we do not. But it turns out that it's not perfect. There is a small fraction of the gas, typically a couple percent, that is able to cool. Now, what does this actually look like? It looks like this. Okay, so let me remind you here, you have a massive elliptical galaxy. And what I'm showing here is H alpha emission, which traces gas that's about 10,000 degrees, so 10 to the 4. And so even if it's a massive elliptical galaxy, these galaxies are surrounded by this cool gas. It turns out that these filaments, these nebula here, are actually highly multi-phase. We can see them all the way from X-ray temperatures. You can see some of the filaments here light up in X-rays. So it goes down from about 10 to the 7 Kelvin down to the H alpha phase and even the molecular phase. Okay, so these nebula are highly multi-phase. And we think that they are the key to understanding how jets heat the gas, but also cause a small fraction to cool. This gas will eventually condense, fall back onto the black hole, reigniting the cycle, and so really creating a self-regulated loop. And so we've been studying these nebula, these multi-phase nebula in clusters for many years now. What's been clear is that they are highly multi-phase. They are made of very thin filaments, some that are as thin as about 70 parsecs, but can extend to kiloparsec scales. So they're very, very thin, long structures. And so we wanted to look into this, and we wanted to understand in much more detail what's going on with this multi-phase gas. How is it connected to the black hole? And so to do this, we targeted Perseus because it's one of the most nearby clusters, which makes it a great target. In addition to being nearby, it turns out that if you look at the H alpha luminosity of these nebula that surround these central galaxies, Perseus is way up here. Okay, so not only is it very nearby, it's also intrinsically very H alpha luminous. So this makes it, again, a great target. In addition, if you look at the size of these nebula as a function of H alpha luminosity, Perseus is way up here. Oops. So again, it's a huge nebula. It really stands out, and we can start learning, how does the feedback, heating, cooling cycle vary as a function of radius? You can really start to explore different parameters here. And so we targeted Perseus. Now, the problem with Perseus, because it is so nearby, it's actually very large on the sky. Okay, so about 90 kiloparsecs corresponds to about 4 arc minutes. This is the H alpha emission here. And so for many, many years, we wanted to know what is the velocity structure of this multi-phase gas. The problem is if you put an IFU on it to look at the velocity structure, this is the field of view of Muse. This is Symphony. It's really huge. You would need multiple pointings. Perseus is also in the north, which makes it more difficult to target. And so until recently, we were quite limited in what was the velocity structure of this gas. There were some long slit observations, some IFU observations in the core, but it was still very limited. Now the situation has dramatically changed with the advent of a new instrument, which is called CITEL on the Canada, France, Hawaii telescope. CITEL is the equivalent of an IFU. And so what it means is that for every pixel in your field of view, you have a spectrum. If you have a spectrum, you can look at the Doppler shift and get the kinematics of the gas. But what really makes CITEL amazing is that it has a huge field of view. It's 11 arc minutes by 11 arc minutes. And so Perseus fits very nicely here. It was initially observed in 2018, and I'll show you what the cube of data looks like through a little video here. So we're gonna go through the cube for the central galaxy in the Perseus cluster in GC 1275. So we just saw the O1 line. Soon we will see the N2 emission, H alpha and N2 again. Then you have this really interesting system, which is called the high velocity system, which is actually a galaxy that's infalling towards the cluster. And then you have the S2 lines. So this was the original data in 2018. So it was the first time that we were mapping the kinematics of this entire multi-phase gas in really great detail. And so this was a paper that came out in 2018 by my PhD student. And since then, we've gotten more observations on Perseus. Recently, we got observations at very high spectral resolution. Okay, so these data were great for looking at the Doppler shift, so getting the velocity map, but it didn't have the spectral resolution to actually look at the velocity dispersion of the gas. It wasn't resolving the velocity dispersion of the gas. Whereas now with a very high spectral resolution, we were able to resolve for the first time the velocity dispersion of this gas. And here's a paper if you're interested. And if I have time, I'll also present some new results that we have looking at multiple emission lines and building BPT diagrams throughout the entire nebula. So let's focus on this result first, which is the main result. And then if I have time, I'll also show you the BPT diagrams. Okay, so this is what we get. Okay, what I'm showing here is the velocity field of this multi-phase gas. Let me remind you why it's so important. You have the black hole here. It has large radial jets. These jets are heating the gas that surrounds it. Most of this gas is heated, but a small fraction, typically a couple % is able to cool and form this multi-phase nebula. What the velocity structure shows is that it's very chaotic. You can go from one pixel to the next, and you can have a very large velocity jump. So it's very consistent with this kind of chaotic flow of gas throughout the entire nebula. So that was the first key result that we got. What's interesting is that Perseus has been observed at many other wavelengths. And so we can compare the velocity structure of the H alpha gas, which traces 10 to the 4 Kelvin gas, so 10,000 degrees, to other phases. So what I'm showing here is the same kind of field of view here of the multi-phase gas. This was data taken with Herschel. So it has a much poorer spatial resolution. I've overlaid in these blue contours the filaments that we see in higher spatial resolution, and the velocity fields match in both images. And I'm just highlighting here some structures that we see. But essentially what this shows is that the velocity of the 10,000 degree gas is very, very similar to the velocity of about 100 Kelvin. So it looks like the velocity structure of this multi-phase gas, as it's cooling from very high X-ray temperatures down to H alpha and even the cold molecular and atomic phase, is it's the same velocity structure. Perfect. Perseus was also one of the few targets observed with Hitomi. And so we can compare, what is the velocity structure of this H alpha gas compared to the X-ray gas. And so the only downside is that Hitomi doesn't have a very good spatial resolution. And so if we integrate the emission in region 0 here, and you compare the velocity dispersion of Hitomi versus H alpha, it's very, very similar. So it's consistent again with the velocity that's from going from X-rays to H alpha to the molecular phase in this multi-phase gas is all the same. It follows the same flow. And soon Perseus will be observed with PRISM. So we are very excited and looking forward to those results. The other key result that came out of this study, besides the velocity structure that we're looking at, is the velocity dispersion. So how turbulent, in a way, is the gas. And this is the velocity dispersion of this multi-phase gas. What you notice is there's this central structure here, which has a very high velocity dispersion of about 160 kilometers per second, whereas all of the rest of the multi-phase gas has this incredibly uniform and very, very low velocity dispersion, about 40 kilometers per second. I'm just going to highlight this feature here, and I'm going to add the radio jets. Oops. There we go. These contours here show the radio jets, just to show where they're located compared to the multi-phase gas. So what we think is going on is that you have the black hole, you have this high velocity dispersion, which actually sits in the wake of the radio jets, but all the rest maintains a very low quiescent velocity structure in terms of dispersion. So if I put this together in a kind of picture, what does this all mean? What we think is going on is that when you have a galaxy and when you have a black hole, if this black hole is driving radio jets, these jets are actually very quiescent. They're not very turbulent. They're not explosive. And they can still heat the surrounding gas. But in doing so, they can also trigger local instabilities that leads to multi-phase gas. This multi-phase gas has a really quiescent velocity dispersion and a very uniform velocity dispersion across the entire structure. The only difference that we saw was in the wake of these radio jets, where what we think is going on is that as these cavities rise, and this is shown also by simulations, there are turbulent eddies that can develop more easily in the wake of these cavities, and this could potentially lead to more turbulent multi-phase gas. And so this is what we're kind of the picture we're putting together of how jets heat, but also allow some gas to cool, but in a very quiescent way. And I unfortunately don't have time for the BPT diagram, but I will take questions now. Thank you.
Julie, for a nice talk. Questions for Julie? Okay, I'll start off with one then. Could you show us the BPT diagrams?
Okay. Yeah. So this is the classic BPT. So one of the really interesting things in Perseus is the multi-phase gas. You can actually see it you can see the whole nebula in N2 and H alpha emission. You can also see the whole nebula in O2 emission, but O3, there's almost none in the nebula. The O3 emission is only concentrated right in the core of the galaxy, which is interesting because in a way, you have to have an ionization source that's strong enough to do O2, but just not strong enough to ionize once more in O3. So there's kind of like an equilibrium, which I'm still not sure exactly what it means. And so one of the things that we do see with the O3 is that there is, even if this is in radio mode feedback, so the black holes are accreting at rates well below Eddington, we do see a trend going from these more star-forming kind of BPT area up to the more AGN as a function of distance from the AGN. And so we do see a trend even in radio mode feedback.
One quick question.
So you emphasize multi-phase nature between H alpha and C2. I was wondering if you can put constraints on like a volume fraction, the mass fraction, relative.
Yeah, so, so the mass in these filaments, the vast majority of the mass is in the molecular phase. So these typically have 10 to the 10, 10 to the 11 solar masses of molecular gas. So most of the mass is there, yeah. Even if they're elliptical galaxies, right? They still have a ton of molecular gas.
We're out of time for more questions, but let's thank Julie again. Our next speaker is Ken Nagamine from Osaka, who will tell us about AGN jet simulations.
Okay. Thank you very much. Thanks for this opportunity, and great to be here. So I'm Ken Nagamine from Osaka University, and I'll talk about AGN jet simulations and get with GAJE 3 Osaka, and also some efforts on the Agora comparison project along this line. So my collaborators, my PhD student, Abid Wiliadi, and also BKO, and the Ji-Hyun Kim, and more to follow maybe. So the previous speaker nicely touched on this two-mode feedback already, so I'm not gonna repeat this very much, but previous simulations have largely adopted this two-mode AGN feedback with some Eddington limited accretion and modulation onto Bondi and Eddington rate. But these are fairly still uncertain. People have extended this model to angular momentum, torque limited models like AGO with GAJE 3. This Bondi rate is modulated by this term using the circular velocity and this viscosity parameter CVisc. And then also extension to the Gizmo Simba runs with different types of modulation here. So it'll be nice to look at the variations of these models to the impact of its to the black hole growth. And I just highlight this one results from this Melanie's previous paper, which we'll probably discuss tomorrow more. But you see these using those models in these different varying cosmological runs, you see largely similar results, which falls into this observed region in the present day universe. But if you look carefully enough on the high mass end and low mass end, there are some significant differences between this SMBH distribution. So on the right, I show two efforts from the Japanese group. Top one is from the Forever 22 simulation that was published in Ejima 22 paper. And it also shows this nicely, this very rapid rise in the SMBH growth around 10 to the 10 solar mass in stars, which we also touched on in the Daniel's talk yesterday. On the bottom, I also highlight one result from our PhD student Yuri Oku's work in a cosmological run. And this is in preparation. And we also varying thermal AGN feedback model using this ego-like model, and different CVisc parameter actually results in this different speed in the rise of the supermassive black hole growth, and also dependency on the seed black hole mass. So it'd be nice to compare all these models in a more standard setting. And one of ways to do that maybe is to utilize a platform like Agora comparison project. And we've been doing this over the past 10 years. Several flagship paper has been published already. In the bottom, you see these 3 papers. We started from this dark matter comparison, and Ji-Hyun Kim published it 2014 flagship paper, followed by the isolated galaxy simulation in 2016. And then on the finally the Zoom run simulation by Santi, Roca, Fabriga. And all these data have been made available to the public on this Flatiron data server here. And also the description is in this archive article. So if you're interested, take a look at that. So to be a very interesting, natural extension to consider this to AGN regime as well. And then most recently, there'll be upcoming 3 papers very soon to the archive. So the paper 4 will be the Cosmo Run 2 about this further analysis of this cosmological run, zooming simulation run with Roca Santi Riga. And then paper 5 will be the satellites. This is about the satellite population in galaxies and halo population at Rescue 2 or so. This is June 23, the graduate student at SNU. And this is already submitted. And one nice bottom line is this no more missing satellites problem in these series of cosmological simulations by different cosmological hydrous codes. And the paper 6 will be this about CGM. It's about circumgalactic medium around redshift about 1, and Clayton Strawn has written a very long, extensive analysis of the CGM properties across all these different code platforms, and it's just been accepted yesterday. So all these 3 papers will be posted on archive very soon. So stay tuned on those. So as I said, it'll be natural to extend this to the AGN regime. So we are slowly working on this isolated galaxy with an AGN. The aim is to quantify the differences in the implementation and consequences of these black hole physics across different codes. And so he was just going to simply implement this massive supermassive black hole seed in the isolated galaxy from the Agora comparison project and evolve it to about 500 mega years. Okay. We're going to take the same incremental steps, and 10 to the 8 is a bit heavy, but when we started with the 10 to the 6, because Milky Way galaxy has 4 million solar mass black hole, but BK didn't see so much of a strong impact on the galaxy itself, so we opted to do a bit more heavy SMBH in this model. So we're going to start with the seeding without the black hole accretion feedback. And then second step, we introduce accretion with Bondi-Hole accretion rate without the feedback. On the third level, we're going to start with a constant accretion rate with the feedback. And then finally, in the 4th step, we're going to implement this full feedback model with a self-regulated Bondi accretion model and the feedback as well. Okay. So we're taking these small steps gradually. So here's an example of the projection plots of the ENSO. In this case, BK took this thermal energy dump within the fixed radius of 160 parsecs. On the left, on the edge, you don't see so much effect of the AGM, but you see this effect of star formation. Galactic wind is actually produced above and below the disk. If you see on the right, you see this temperature is having a galactic wind effect. And on the most right column, you see this no star formation run with the AGM effect. So from the central part of this black hole, there's a quasar-like feedback applied, and the CGM is heated to very high temperature by the AGN. Okay. We can also look at the phase diagram like this one, velocity weighted, to highlight the impact of the outflows. On the left column with the star formation, you see this galactic wind feedback pushing the gas to low density, high temperature gas. In the middle, you're supposed to see the AGN effect, but the number of fluid elements impacted by the jet itself is a bit low, so you don't see a strong impact, but there are some feedback effects by AGN as well. Okay, so in terms of SPH, we have been doing the same thing on the gadget runs. So starting from the AGN, no AGN cases with the seeding and black hole accretion only. And then we also considered various treatments going to the feedback, but in the case of SPH, you have to do a little bit of more treatment, trying to do the similar effect of the feedback, just like in the mesh simulations. So there are few trials have turned out to be not so great. In the end, based on the higher resolution jet simulation that I'll show later, we eventually sort of settled down on spawning the thermal bomb method, which we call STB model with constant accretion. Also the thermal bomb with self-regulated Bondi accretion, just picking a nearby particle near the black holes, or the kernel-based energy deposition, similar to other people are doing, will self-regulated black hole accretion. Okay, so here's an example of those methods using from the gadget runs. On the left, this is the spawned thermal bomb method. You see this bipolar nature of the outflow, similar to radio jet. And on the right, you see these two panels are the no star formation, and you also see the high heated gas both above and below the disk. Okay, So at least we can show that these are working. And if you look at the phase diagram on the gadget runs, it looks a little bit different from the ENSO runs. But if you have a star formation, this high density, low temperature gas is kicked up to this intermediate multi-phase nature of the gas. And then also with the AGN and galactic wind of the supernova, they also get kicked up to this low density, high temperature gas as well. On the right panel, there's no star formation. So in this case, directly the AGN feedback is kicking in, and then the gas in this high density central region is kicked up. And if you wait until the later phase, you see these hot red dots actually being pushed up and then raining onto this low density hot temperature phase. So examining these phase diagram across different codes, you saw the burst of the AGN feedback there, pushing a lot of gas onto the low density regime. Okay. Now, those are good comparisons, but you can learn more from the higher resolution simulations. So there's been a lot of work along this line, not just cooking up these subgrid models of AGN feedback, but we can try to study jet itself with high resolution runs. So there's been effort by Boren-Sijaki 17 using a repo, and also the jet ISM interaction using Pluto code. Martizzi used Athena code. We also heard this morning of the CR-driven jet using Gizmo from Sue's work. And also there has been also work using the Swift SPH code by Haskell and Lacey as well. So in our group, we also following the Haskell-Lacey method, largely following their simulation setup of this idealized jet setup. And then here we are able to reproduce largely their jet simulations. So looking at physical quantities like the temperature, density, entropy, pressure, ramp pressure, and Mach number, we can study the closer structures. Yeah. Okay. And in this comparison, you can study this jet evolution, and there's a nice analytical formulation where you can look at. And if you start to compare in more detail, the details of the jet structure start to matter. So we're examining like the jet lobe radius and the jet lobe length, cocoon length and cocoon radius. There's a nice analytic solution where you can, by Kaiser and Best, which shows this length of the jet is proportional to T to the 3/2 if you have a constant ambient density. And then there's two length scales you can also come up with using the physical quantities near the black holes and then in the ambient mass, characterizing the regime of the jet propagation, starting from the ballistic expansion, and it settles down to this after strong shocks. You go into this self-similar regime, and then it gradually slows down later on. So between these length scales, our jet roughly follows this self-similar result, although it's a bit steeper than this self-similar solution, but more or less agrees with these analytic results. Okay. So I will end with this entropy pressure diagram. You can also look at entropy generation. So as soon as the gas is, the jet is ejected from the central black hole, it starts to shock. So the gas is starting here, but it gets shocked up and then later eventually lands on this pressure equilibrium region. So by looking at the structures of the jet, we can learn more about the jet structure itself, and then also relate this to the galactic simulations, and then further check the physical validity of our models. Okay, and we can decompose this jet structures. This is a total distribution on the phase diagram, demonstrate temperature plane. These are the gas that is launched from as a jet, and also the shocked ambient gas to the high temperature by the jet itself. So these decomposition can be done using these high-res simulations, and possibly compare to observations and learn more about the interaction with ISM. Okay, so one final slide on the artificial viscosity method. In the SPH, you have to implement this AV to capture the shocks. And so we are using this time-dependent approach taken from the cosmological runs. But if you do a previous standard method or conventional SPH methods, they actually tend to have a faster jet evolution, and they seem to be a bit incorrect compared to the self-similar result. So AV also matters, and it's a cautionary remark for the SPH community. Okay, so we'll stop here and take questions, and hopefully maybe some other codes will join this comparison project on AGN front as well. Okay, thank you.
Thank you very much. Questions for Ken?
Thanks. This is very nice. Do you want to say a little bit about the jet properties for the comparison and how you chose them?
Right. So actually, it's kind of still very artificial in these parameters. So in this initial comparison, like in these simulations, we basically followed the Haskell-Lacey parameters, and the central black hole is there was parameter here. Yeah. So initial condition is this ambient constant density, ambient medium, temperature of 10 to the 7 K. This is a bit too hot compared to the galactic simulation that we do. Gas particle mass into the 5 solar masses, dimension of this, particle number like this. And there's an equivalent reservoir about 10 to the 5 solar mass, half open angle, 10 degrees. And then the jet power is set to 10 to 46 ergs. So this, if you have a constant accretion model, it kind of continues to inject lots of energy into the ambient medium. So that's also a bit unphysical. But you can also do the self-regulated accretion as well, like I showed at the SPH simulations. So it's by no means completely physical model yet, but we're just starting from this model that we can take from.
Thank you. So I was wondering if there is anything that could bind the jet as it comes out. So I was looking at that extent. It's like 1,000 kiloparsec. That's very far away. So yeah, is there some gravity force?
Yeah. Yes, there is a ambient dark matter density potential, of course. Mimicking the Milky Way type galaxy in this particular case. So you're talking about this high resolution case. So in this case, this is just a uniform density background. So it's now not really bound, and you're just injecting the very strong jet into the ambient medium. So if you want to stop it, you have to turn off the jet and energy injection in the center. So yeah, in that sense, this is also a bit unphysical in some sense, but yeah, it just gives you a more detailed structure of the jet itself, like internal structures of the jet itself. So it kind of provides you a different direction to analyze the jet. Yeah, but hopefully we can build up on this and then implement this model into the galactic simulations and come up with a better model of the jet propagation. That's the purpose, I think. Yeah.
Thank you, Ken. We're out of time for questions, but please ask him more later in the break. Let's thank Ken again.
Okay, thanks.
And up next, we have Marion Farsi.
Okay, so hi everyone. I am, so in French, Marion Farsi, postdoc at EPFL. I don't know if that works. Well, okay, perfect. And I'm going to talk about radiatively efficient AGN winds, which is a work doing in collaboration with, with people, most of them being attending this conference actually. But so first, to give a little bit of context. So this is the timeline of the universe, where we start with the Big Bang on the left and where time increases from left to right. And so this is just to remind that at present day, we have a pretty nice understanding of what's going on galaxy evolution. And in particular, in very massive galaxies, we tend to observe and know that they all host a supermassive black hole in the center. And that there is a coevolution between these beasts, these black holes, and their host, which is something we can see, for example, which this famous scaling relation showing the evolution of the black hole mass with the stellar mass of the host. But then it's very unlikely that so the black hole activity and back reaction, so what we call feedback on their host galaxy, will remain constant through cosmic times. And so one nice avenue for better understanding how black holes work, how they act, how feedbacks work in galaxy evolution is to have a better look at the high redshift universe, and in particular when the first galaxies and black holes formed. So that's what encircled here, a few billion years after the Big Bang. And so we already know that black hole activity is different through cosmic times. And I'm throwing here black hole evolution as a function of the barometric luminosity, basically to show that a given black hole mass at high redshift, so that's quasars at redshift above 4, they tend to accrete gas at a very high rate, so almost at the theoretical Eddington limit. And so now is a particularly special epoch to study the high redshift universe. Now that we have, so that's just 2 examples here, but in particular with the James Webb Space Telescope, which is probing as a formation evolution of the first galaxies. But this is also unveiling a few new key questions that are still unsolved right now. So for example, how do black holes can acquire such high masses so early after the formation of the very first galaxies? How AGN feedback is going to act on these galaxies when they form? And in particular, how can massive galaxies form and yet be quenched as early as a few giga years after the Big Bang? And I'm going to focus on this one just to give a bit of context of why we should be careful about the radiatively efficient black hole regime. So this is showing the number density of massive quenched galaxies as in different, so this is a collection of observations. And this is the same number derived in state-of-the-art simulations, so in a given fixed volume. And now with especially the James Webb Telescope, we are measuring more and more of these very massive galaxies that are barely forming stars anymore. And so in simulations at high redshift, so especially beyond redshift 3, we barely simulate this kind of objects, which is kind of puzzling, and ask the question of why can't we simulate these objects? So we think that AGN feedback is responsible for shutting down star formation in our local universe. But why is it inefficient in simulations at high redshift? So that's the 2 key questions I'd like to talk about today. And for that, I'm going to first focus on a study that has been done by Shalini Kurenchi, who is an undergrad student. And so what she has done is to focus on the Illustris TNG suite of simulations, so that are cosmological simulations with boxes between 50 and 300 megaparsec in width, with hundreds of thousands of galaxies. And she focused particularly in massive galaxies and distinguished 2 samples of star-forming galaxies and quenched galaxies here based on their specific star formation rate. So here I'm going to show only a specific sample of galaxies selected at redshift 3.7, which is the first snapshot in this simulation where we do observe quenched galaxies, while we do observe quenched galaxies at higher redshift. And so the questions was, okay, what could be responsible for shutting down star formation in these objects? And one naive explanation could be, okay, so when we have galaxies merging together, we have so fueling gas arriving, which could create a starburst, and after which no stars could be formed for a few million years. But it turns out that comparing the number of merger events in the 2 samples of galaxies lead to very similar results. So meaning that it's unlikely to be responsible for quenching galaxies in this simulation at high redshift. And then another thing we've looked at is the large-scale conditions, so the environment. Looking at, for example, for so the mass of the halo host of these galaxies, and for how long do they spend? So that's the fraction of galaxies in each sample, blue being the star forming and red the quenched, and the time spent in halo most massive than 10 to the 12 solar masses. And so from this plot, what you can see is that in average, quenched galaxies tend to reside in most massive environments. And so it's not shown here, but also in denser environments. And this has some consequence on black hole growth, actually. So that's now the black hole evolution as a function of time. So time is increasing from right to left this time. And so again, in average, so the black hole tends to grow faster in the sample of quenched galaxies, probably because there is more gas available for black hole accretion. And so because the black hole grows faster, the quenched galaxies are exposed for longer to AGN feedback activity. And so what is this AGN feedback? How is it impacting the galaxies, basically? And so what we realized looking at the cold gas content around the galaxy, so that the cold gas fraction as a function of time, and also outflows or inflow rate around these galaxies. So in general, the quenched ones have much lower cold gas fraction, so less fuel for star formation, and also have larger outflow rates and at the same time less inflow rates while being in more massive environment where gas could be potentially more likely to be accreted through the cosmic streams. So this tends to show that AGN feedback do also have a role in regulating star formation at high redshift. But then what makes the difference between star forming and quenched galaxies? Because here we are only focusing on massive ones and they all host a supermassive black hole in their center. So what I did was to resimulate a few galaxies from each sample, and I'm here focusing only on two specific cases. So that's zoom-in simulations of quenched galaxies at redshift 3.7 and a star-forming one. And here I'm showing the star formation rate as a function of time. The black curves are the fiducial TNG physics, and in red I'm showing the counterpart where we turn on when we don't see any black holes, so no black hole accretion and no feedback. So for the quenched galaxy, what you can see, so here in black is so the shutting down of star formation beyond redshift 4. And in the dotted vertical line, I'm showing when the radio jet feedback mode is kicking in. And so this coincides quite nicely, which tends to show, and it's not the case for this specific galaxy, but also for all the others from the sample, that quenching coincides with the triggering of the AGN jet mode. While for this specific galaxy, which is still star forming at high redshift, there is no dotted line because it's still in the quasar mode, which tends to show here that it's relatively inefficient in suppressing star formation. And so this may have, it may have to do with how we model actually this feedback in those two regimes. And as maybe a reminder, because it has already been discussed a bit before, but in TNG and as in many other simulations, so AGN feedback is modeled in a dual way, let's say. So when the accretion rate of the black hole is relatively high compared to this value, we are in the quasar mode, and then feedback is injected in all gas cells around the black hole as an isotropic thermal energy deposit. While when the accretion rate is relatively low, this is a kinetic energy deposition that is done, and every cell receives a velocity kick in a random direction. And so that's my point here. So this quasar mode in the TNG simulations, for example, is relatively simple. So modeling this feedback with just thermal energy does not reproduce the complexity of reality, for example, and we do not really reproduce observed AGN winds. So this is a quite simple way to model how AGN feedback works. And this might be responsible for not reproducing, for example, the fraction of quenched galaxies that we observe at high redshift. So to confirm that, one thing I'm working on is to try to improve this prescription and go for relatively efficient black hole winds, try to better model these things. And for that, what we are doing is to rely on the implementation done in the gadget code, developed first by Jeremy Ostraker and then by Ina Choi, and to port this implementation into the repo code together with the TNG physics. And so the idea here is to not only input energy, but also mass and momentum. And so maybe quickly, just to show you a bit how this will differ from the current implementation, you can maybe skip that. But so that's what's done in TNG right now, isotropic versus random kinetic jet. What we now want to do, and so the status of the implementation that has been called Mistral, because that's the name of a wind, is to, so in each cell around the black hole will receive a velocity kick radially away from the black hole, with a strength that depends on their mass, their distance from the black hole, and their alignment with the average angular momentum, so that we want to have this bipolar wind emerging instead of just choosing random directions. And so that's preliminary results from this current implementation that is tested right now on an idealized galaxy. So this is a Milky Way mass galaxy with ICs taken from Kumgi in Gizmo and adapted by Brian for the ARIPO code. So that's how it looks like in density, face on and edge on. You have here a few numbers about the masses and resolutions that we achieve. And so here, that's basically the difference in temperature map of how the agent feedback is impacting the galaxy. So when we only have thermal energy inputs, we barely see any wind emerging. It's just puffing a bit the galactic disk. While right now with this Mistral model, we do observe an expanding wind, relatively hot wind going out of the galaxy. And again, quite quickly, if we compare a few key properties of these galaxies, so stellar mass, black hole accretion rate, and black hole mass. So in blue, that's with the current TNG implementation, and in purple with the new one. So you globally, these quantities are quite similar, and you might think that the stellar mass and black hole mass are different, but here you should have a look at the y-axis. So they only differ by 10 to the 6 solar mass in general. So this is still in progress, and obviously to test this implementation, one need to go for a cosmological setup, and in particular test this via zone simulations at redshift 0. So that's the next plan. And as I don't have time to go through this one, okay, I just emphasize that right now in simulations, in particular in TNG, only the kinetic mode is really efficient in suppressing star formation, and one might try to maybe improve our prescription for the relatively efficient regimes. Before, we have put a lot of efforts into producing the local universe and scaling relations. Now that we do have a clearer view of what happens at high redshift, it forces a bit also trying to better understand evolution at high redshift. And that's future plans. And yeah, I'm happy to take questions if you have.
Thank you very much. One question already.
This is really great. Thank you. So for the Ostriker and the Choi work, I guess my question is about your velocities that you're going to choose.
Yeah.
Because in those papers, they choose quite a high velocity. It's like 10,000 kilometers per second from like BAL wind observations. But those observations are on like very small scales, right? As you go out further, it's like a kiloparsec or something. You get down to like 1,000. You see winds of like 1,000 kilometers per second. So which velocity are you going to choose? Because 10,000 will probably do something because it's so strong. But is that the correct velocity to choose for the scale of your simulation?
So yeah, indeed, that's one of the two main free parameters of this model. But we won't end up with a wind at 10,000 kilometers per second. So that's the target velocity of the wind for some scale that we don't resolve at all. So that would be for the BAL winds indeed. But then we distribute the energy, kinetic energy corresponding to this chosen velocity, and we end up with much smaller velocity for imported in each given cell. So yeah, we won't reach this high velocity at all. Yeah.
Cool, thank you.
You have another question for Marion? I mean, I do, but.
So are you saying that your isotropic thermal energy injection does not produce bipolar winds? Because that seems to be quite different from what everybody else finds. And I'm curious about whether you understand why that's the case. Because you do have like, just a path of least resistance, right? So why does?
Yeah, so what, from the map I've shown here, it's not the case, but I believe it depends also on the feedback coupling efficiency maybe with gas. So for example, I know Eagle is only injecting thermal energy, but yeah, then probably how because the energy is determined from the black hole accretion rate, but then in this specific case in TNG, only a small fraction, I think it's 2%, is coupled to gas. And this is probably not enough to create those winds that could emerge with another implementation. But these numbers have been calibrated to match scaling relations so that the black hole can grow with a more or less physical way, and but down to achieve zero again. So that's why it's more here about the relatively inefficient mode being effective than this quasar mode. And
I'm afraid that's enough. That's the time we've got for questions. So let's thank Marianne again. Now we have some rapid talks, starting with Greg, who you can get your own slides up. I'll give you 1 minute warning.
Great, thank you. So in my short period of time, I want to rapidly make 2 points. The first point is just an analytical reminder, actually, so coming from work that Kang Yi has done, Rainer Weinberger and others. And I just want to make this point that for these jets, which have intrinsically narrow opening angles, there are really 2 quantities which matter. So the total amount of energy and the momentum content. And so the ratio of these 2 things determines the opening angle of the jet, eventually how isotropic it becomes. And so low momentum jets, the speed at which the jet propagates is dependent on the momentum flux. And then that energy the momentum is thermalized, and that drives transverse shocks outwards. And so it rapidly can isotropize if the momentum flux is light enough. Why is that an appealing quality? Well, because isotropic jets will heat material both in the direction that the jet is propagating, but also transverse to the jet. So that's an easier way to regulate inflow and heat gas at large radius in particular. So the second thing I wanted to talk about was an examination of these kinds of light jets in a cosmological simulation. So this is some work done by Tianhan Liu, who's a graduate student at Columbia, myself and Jerry Ostreicher. And we took ENSO, an AMR simulation. We added a black hole accretion, added some refinement around the black hole to make sure that we could get down to roughly the Bondi radius, and then ejected jets with a fixed efficiency. And we explored 3 simulations, one where we added the black hole, but there was no accretion or feedback. And then 2 more where we used 2 popular prescriptions for the accretion, one based on the classic Bondi-Hoyle prescription rate, and the other this torque based accretion rate. We actually found that if we chose appropriate parameters, we could match reasonably match so we ran one 10 to the 13 solar mass cluster, which for these particular runs were roughly on this stellar mass halo mass relation and the black hole stellar mass relation. So how did they go about doing that? I think that's the interesting thing. So as you can see here, the black holes grow, and in both cases, basically shut down star formation at late times. The way they do that is kind of interesting. What you can see here, so this is a timeline of evolution of the halo. And just to remind you, these things have a virial radius of around 400 kiloparsecs. So this is out to large distances. This is the entire circumgalactic medium as a function of time. And this each point here is radially averaged. And so what you can see is this is for the hot gas in particular. The thing I want to emphasize here, which is absent in the low accretion case, is the strong shocks, which propagate out to large distances. So that heats the gas at large distances, and particularly for the hot gas, prevents it from flowing in. So this is the inflow rate for the case with no accretion, and these are the case with either of the black hole versions. And so one thing I want to emphasize is the outflow rates hardly change. So these things are not ejecting a lot of gas. Instead, that energy is going out, heating CGM at large distances, lifting it, as Brian emphasized earlier, and then setting up, preventing this inflow. So I just end with this, which just shows the inflow decrease here as a function of radius, averaged over all of the simulation outputs from redshift 1 to 0, 0, 1 to 0. And then this is the outflow increase. And in fact, what you see is the outflow, in fact, decreases. There's less gas which makes it in, and so less gas that comes out. Thank you.
I believe we are going to do both of the rapid talks and then have questions afterwards. So where is she? There you go. So our next rapid talk is from Ruth Daly.
All right, I'm going to talk about the contribution of the rotational energy to total black hole mass for all black holes, but I thought I'd focus on supermassive black holes because that's of interest to the group here. Okay, so there's a lot on here, but I wanted to remind everyone that when you measure a black hole, the total mass that you measure has two pieces. One is the irreducible mass that cannot be decreased, except by Hawking radiation, which is not important for any of these black holes, and the rotational mass energy of a rotating black hole. For a maximally rotating black hole, these two terms are equal to each other, okay? So if you're doing a simulation and you're looking at the rest mass that is collapsing into a black hole, the black hole mass can be significantly larger than that irreducible mass. There's another quantity, and I wrote that down here. Since they added quadrature, if you have a maximally spinning black hole, the rotational mass is equal to the irreducible mass is equal to 0.7, around 1 over the square root of 2 of the black hole dynamical mass. What we measure when we study black holes is the total dynamical mass. So if you look at the motion of stars, gas, anything around a black hole, you're measuring the total dynamical black hole mass. Now, if you know how rapidly a black hole is spinning, this is the dimensionless spin angular momentum is a piece of this term here. If you know how rapidly the black hole is spinning, you know the rotational mass. And I wrote that down here, I hope. Well, guess I didn't. I think I have it on the next slide. Now, another quantity of interest is how much mass energy is available to be extracted, for example, to power jets. And it's a different quantity. It is not, it's only part of the rotational mass that can actually be extracted. So the spin mass energy that's available to be extracted is the total dynamical black hole mass minus the irreducible mass. And of course, all these equations go way, way back and are very, very well known. So it is possible to decrease the mass of a black hole by powering outflows. Now, these relationships are generally written in terms of the dimensionless spinning momentum A star. And there are several reasons why it's good to move away from the dimensionless spinning momentum A star, because this always enters as a square root of 1 minus A star squared. So A star can never be greater than 1. But we have these things called measurement uncertainties. So we have to allow for values greater than 1. So it's much better to work with what's called the spin function. And I was happy to see this in one of the talks earlier today. Someone had written all the equations in terms of the spin function, which is the dimensionless spin angular momentum divided by 1 plus the square root of 1 minus A star squared. It turns out that this quantity capital F is equal to the ratio of the rotational mass divided by the irreducible mass. And you can also write the relationship between the dynamical mass and the irreducible mass in terms of the spin function. And you can write the spin mass energy available to be extracted in terms of the spin function. The spin function is something that I have determined for over 700 supermassive black holes with the outflow method. And it does sometimes exceed unity because of the measurement uncertainties. So for a sample of 100 FR2 sources, which are classical double radio sources, the big giant double sources with redshifts between 0 and 2, I determined that this is the distribution of log F. So a maximally spinning black hole would have log F of 0. This is the part of the distribution of black holes that are maximally spinning. So it turned out about 2/3 of the black holes in that sample are maximally spinning, and 1/3, which you get by subtracting this off, are less than maximally spinning and have a broad distribution of spin values. I'm almost out of time already. Well, then let me go on to something that there's tons of energy available to be extracted from black holes for this sample going out to a redshift of 2. I thought you might also be interested in this result. And this is how much energy is extracted per outflow event for each of these FR2 sources. And interestingly, the total energy extracted per outflow event relative to the total black hole mass has a small value, about 3 times 10 to the minus 3, or minus 2.5 in log space, and a very, very small dispersion. So this is what I got for this sample of classical double sources going out to a redshift of 2. I was reading an article by Donahue and Voigt and noticed they have pretty much the exact same number for a completely different method based on low redshift sources in clusters of galaxies, basically the expanding bubble sources. So we're getting very, very similar numbers. In the case where I present this in my 2022 paper, I gave 5 or 6 explanations. One explanation is only, this is really could be interpreted as an efficiency factor. Maybe only some small part of the energy being extracted from the black hole is going into the jet, and the rest of it is being lost in other avenues. And I'm out of time. So thanks.